Hello, everyone. Okay, so in the previous video, we focused on talking about nitrogen processes that can occur in our shallow soil zone, including the soil leaching process, as well as the plant nitrate uptake. So in this video, we're going to move on to start looking at the deeper zone and focusing on the process of denitrification. So denitrification process involves the conversion of nitrate to N2 gas under anaerobic conditions. And for our BioRT reaction network, we have implemented within the relative D zone because there is a more consistent water storage throughout the year that can facilitate a more anaerobic condition to become favorable environment for denitrification processes to actually occur. The BioRT reaction network is set up as the following, where we have the soil DN solids representing the soil end phase of denitrified microbes. We have our DOC to signify the electron donor for the denitrification processes, as well as our nitrate for our electron acceptor, and then producing into aqueous being produced and also being released into the soil. So the denitrification process is being modeled using this dual Monod reaction rate. Here we have the reaction rate is defined by this reaction rate constant again. We have our surface area again, and then we have these dual Monod terms where we have the concentration of the DOC for our electron donor, the concentration of our nitrate serving as an electron donor. We have this new term, this oxygen inhibition term, to simulate the necessary anaerobic conditions for denitrification. And then we have the function of temperature and the function of soil moisture again. However, since this video series, we're really only trying to get a sense of how the BioRT-HBV model is actually ran. So we are going to do some of the simplification to make the process a little bit easier by making some of the assumptions. The first assumption we're going to make is that DOC is going to be abundant and causing it to not be a limiting factor for denitrification processes. And thus we're able to get rid of this Monod term here. And then the second assumption we're going to make is that it's going to be a total anaerobic condition within the deep zone. So we can implement this reaction where there will be no O2, which then gets rid of this oxidation inhibition term. So with these assumptions, we're able to simplify our whole reaction rate law to become something we have been familiar with from the previous videos. So once again, we're gonna need to set up our input files to simulate the denitrification processes. In my previous video referring to the shallow zone processes model setup, in this video series, I went into details talking about the setup of the necessary alternate input files. So I won't be going into details again with this video, but only pointing out some of the necessary important key points to keep in mind. So the first input file that we need to alter is this chem.txt file. We need to again check that we had turned on our reactions and then listed out our primary species. So in this case, we have the nitrate, the N2, and also the soil DN. This is reflecting the assumptions that we made in the simplification that we have done, only needing to keep track of the necessary N species. pH is included again because it's a requirement for the model to run. We then have again our mineral kinetics with the soil DN, and that is labeled as a default, referring to the default in the database file that reflects the assumptions that we are making. So the next input file that we need to alter is the CINI file. We then again have the species listed out under the 3 different zones: our precipitation, our upper zone, and our lower zone. And then we have our soil DN as our mineral solid phase. And then we have the corresponding reaction rates listed out. Since we are implementing denitrification processes within the deep zone, it is important to see that the concentration and the SSA value is much higher in the deeper zone in comparison to the upper shock zone. Lastly, again, we have the precip chem in the num-EXP precip chem to be altered again. Again, there should be a separate column of the time steps for each species listed, and the precip chem txt file should be exactly the same as your num-EXP precip chem file. So with that, we are now ready to we are ready to run the model. So once again, I'm going to open up my Linux terminal. Can we see? Let me pull that up. Okay. And there we go. So once again, I'm using the supercomputer Roar to run my code. If you are using the executable, this might slightly look a bit different. So hopefully it's working now. And then here we go. We're going to type in /BioRT to run our executable. What is going on? 1 second. Okay, round 3. Hopefully it works now. Nope, never mind. Now it should be working. All right, so typing in our /BioRT for executable, and then we're going to list out the folder name that we have our input file stored under, which in this case is called denitrification. Okay, and once again, we see that the model is reading in our alter input files. And then we have these 4 lines indicating the model simulation started, simulation succeeded, as well as a numerical experiment started and succeeded. So with that, we're going to jump over to look at our output file. And once again, we're going to look at the one that's labeled as the num-exp.txt file. And here we are. So looking at the model output file, once again, we're going to check to see that there is no NaN values within our times steps. And the species that we indicated are presented in the different zones, as well as that we have the reaction rates at the end of our output files. So with that, we are now ready to plot some of the results, which I have already done, just to save some time. And here, let me see, let me jump back into my PowerPoint. Okay. So let's start by looking at the nitrate concentration in the 3 different zones. So you can see that nitrate is, on my print laser pointer. We can see that nitrate is coming mainly from the upper shallow zone with the seasonal fluctuations, and then the nitrate coming from the lower zone, the deeper zone is much lower in concentration without as much of a fluctuation. The C nitrate concentration is then an intermediate concentration between the upper and the lower zone due to the dilution effect from discharge. If we now look at the N2 concentration, one of the big things that should pop out to you is that N2 is being produced from the deep zone and not necessarily coming from the shallow soil zone. Extreme N2 concentration is then a dilution effect of all the N2 that is being produced out from the deep zone.